Please respect the speaker while you're in here. Silence your cell phones. Otherwise, enjoy the presentation.
Cool.
Oh, yeah, you get the microphone.
I have a microphone. Hi. It wasn't like document number 1 to document number 2. It was just a random number that was being generated, right? And it was a fairly large random number to where you wouldn't want to be able to brute force that. You absolutely couldn't brute force it online. You couldn't send like a request every single time. And he was just using like the standard insecure random number generator. And so this is normally where, as a penetration tester, the finding ends. We say, well, the random numbers are being generated insecurely, and maybe if we had a tool to actually break this, then we would, you could theoretically grab everyone's documents. And I thought that's something we could do. It seems like a reasonable sort of thing. And then kind of spent a long time searching for such a tool, and it turned out that nothing actually existed. There's a lot of cool tools that are proof of concepts that do one very specific thing with random numbers that break them, given an entire set of assumptions that are not really usable in the real world, that can't actually be used to break real web apps or applications generally. So we wanted to make something that was actually very practical, something you can use to break real websites using real random number generators that aren't some trivial ones that are made just to kick over. These are actual generators that are being used by all the major frameworks. And so that's how this whole sort of thing came about.
Yeah, and then probably about 6 months later, I needed to do the same thing in a Ruby web application. So Dan sort of started the project, and then I came along, and I'm responsible for a lot of the threading and the addition of a couple more PRNGs and stuff like that. And we've been collaborating on it for a while now. So.
Okay, we'll get into a quick demo just to show you what it looks like, and then we're going to talk a little bit more about it, about how it all works, and that sort of thing afterwards.
Oops, they mirrored now.
It mirrored suddenly?
It mirrored it, yeah.
Okay. Projectors.
Okay, so we have some output here from the Mersenne twister, which is the one that we're going to be demonstrating here. This is the direct output of the Mersenne twister. A lot of times, this will be the basis by which a password is generated or something like that. So, but these actually are also not sequential outputs, or I don't believe they are. These are just several outputs that we've gotten from any application which uses this random number generator. And there it found the seed.
So yeah, you can see in the bottom here it says it found the seed 31337 with a confidence of 100%. So it looked at the numbers that it observed there. So the idea is that you would be looking at whatever numbers are output from whatever program you're seeing. They're here in decimal, but it'll take it equally well in hex or whatever the actual application takes, right? And we'll talk a little bit more about mangling scripts in the case that if it's a generated password. But this is just an easy example of how you can take some output from a random number generator, throw it into the tool, and then the tool will give you the initial seed that was used to generate those numbers.
Yeah, and as you can see right there, I deleted several of the numbers. So it doesn't have to be sequential outputs. As long as they're, coming from the same seed, we can reverse that. And normally, I should also probably make the point, it takes a bit longer than this, but this is an example. So for the sake of time, we've chosen a particularly weak seed. But you can brute force the entire seed space pretty quickly since it's threaded. So.
Okay, yeah, we can come back to the program again after we explain a little bit more of the inner workings of it. So that's kind of what it looks like. So you're getting the actual output from a random number generator, just the raw numbers that it outputs, and then you're getting the initial seed. And from the initial seed, you can then predict all future and past random numbers that are going to be generated from that seed, right? So if that's a password, then you're going to be able to get everybody's randomly generated password. If it's a document ID, you're going to get everybody's documents, et cetera, et cetera. So it's going to be dependent on the context in which it's used, but this sort of thing is obviously almost always a a very important thing from a security standpoint.
So before we get into how that program actually works to recover the seeds, we're going to talk a little bit about what is a pseudo-random number generator and what, sort of define what that is. Talk a little bit about the history here to sort of set the stage for breaking these. So in nature, there's a lot of random sequences everywhere. However, and so traditionally what you'll do is you'll do something called sampling. And you'll sample this noise. For example, the static on a television is an excellent source of real randomness, truly random data. So you'll sample this to produce numbers, and then you can use these numbers for whatever you need random numbers for. This is called a non-deterministic algorithm, I guess, because we're taking a non-deterministic source of information and converting it to numbers. Machines, on the other hand, are very deterministic, and computers fall into this category. Their processes are repeatable and predictable. So this is, machines are deterministic by definition. Computers wouldn't be very helpful if you ran the same program on different computers and it did different things half the time. Although sometimes that happens with race conditions, but for the most part, machines are very deterministic and they do the same thing every single time. So the first random number generator was actually developed for the ENIAC for calculating certain equations related to the development of the hydrogen bomb by someone called John von Neumann, a mathematician who was working on it at the time. And basically he needed to repeatedly do calculations related to the hydrogen bomb. To do these, he needed lots of random numbers, but the ENIAC had very limited memory space. So you can't take a truly random source and store all of those integers and do multiple calculations because the machine didn't have enough memory. So he developed what's called the middle squares method, and this is the first random number generator. There's a lot of different kinds of random number generators. This is just the first one. And that is you take some truly random value called the seed, and you simply square it and output the middle. This is where it gets its name, the middle squares. And whatever that output is becomes the next seed, and you square that and you output the middle. And you simply repeat this process indefinitely. Now, eventually, this will repeat when it gets to a seed, which it has previously used. The amount of time it takes for a random number generator to repeat is called the period, and we'll talk a little bit more about that in a second. But really, the point here is that in nature, a truly random source is from sampling non-deterministic data, whereas a pseudo-random data is collected by introducing a seed and then getting output from a deterministic algorithm. So that's really the difference that we're looking at here. And we're going to talk a lot about the period as well as the seed, because those are going to be really critical to the randomness of the data. So this demonstrates the period. This is called a random walk. So basically we're taking output of a random number generator and drawing the line, and the line changes direction based on the output of the random number generator. The white line is from truly random data, and the blue line is from a pseudo-random number generator. And you can see that the pseudo-random number generator repeats itself over and over again, whereas the truly random source just sort of walks around indefinitely. And the key takeaway here is that with a pseudo-random number generator, there are many sequences which cannot occur, and that's one of the properties that we can use to recover the seed. And we'll talk about how we do that in a little bit here. So period size. The Mersenne twister has a very, very, very large period. This is the number here. This is how many sequential outputs you can get from the random number generator before it will repeat, which is basically infinite. There is not enough energy left in the universe to cycle the Mersenne twister with a given seed through all of its iterations. So that's one important property. However, the Mersenne twister is not cryptographically secure, as hopefully we all know. So the period size isn't everything. Even though this has a very large period and it creates very good randomness, it's not suitable for cryptography.
That point actually is worth emphasizing as well, actually, that the depth of any random number generator is, for all intents and purposes, infinite. Like, even though, strictly speaking, given enough time, this could, like, repeat, right? Like, for all intents and purposes, it's infinite, right? So given a particular seed, and you say, just generate me random numbers, it'll just keep on doing it functionally infinitely. So that's going to be a challenge of ours, as we'll kind of describe a little bit later.
Okay. So now let's say we have a random number generator, and it has a very large period, which will never repeat, and we get a bunch of output from it. How can we determine whether or not that output is good randomness, right? We're using a deterministic algorithm to create to simulate non-deterministic data. So how can we sort of evaluate whether or not they have, similar properties? And it turns out that we can actually do this using something called the die-hard tests.
That's actually its name.
Yeah. It came out the same year as Die Hard with a Vengeance, number 3. Although, personally, I like Live Free Die Hard the best.
I guess that's why we're not actually sure that's why they called it that.
No, but, it's a
Well, we'd like to think.
So, there's a bunch of different statistics that you run against these random number generators to see if their output resembles non-deterministic data. So an example is like birthday attacks. This test suite will look for collisions like that. The craps test, which is pretty cool considering we're in Vegas, it basically simulates a bunch of games of craps, like 100,000 games, using the output of the random number generator, and then sees if the outcome follows a certain distribution.
And that's a pretty important use case too, right? Like, people that are trying to implement random number generators for the purposes of running online gambling sites really want to make sure that, like, if you're going to run a craps game on the basis of this random number generator, that it's going to be fair, right? It's not going to, like, give the house a bump, or, well, they wouldn't mind that, I guess. Make sure that it would give all the players a bump or something like that. So we want to make sure that, like, given certain realistic applications, that the generator is going to be fair.
And then another one that I like is the monkey tests. And this is the old, like, if you have an infinite number of monkeys banging on a typewriter, you get all the works of Shakespeare. So what you do is you take the output of the random number generator and convert it to words, and then see how many English words actually come out. And that should also follow a certain distribution, and if it doesn't, we know that the data is not truly random.
Yeah. And we should expect to see words, right, like by the infinite monkeys theorem. But we shouldn't expect to see, we should expect to see a very specific amount of words.
Yeah, there's a certain distribution that you look
exactly.
for. So the Mersenne twister, which is the focus of this talk, I guess, passes all of these tests, and it has a very large period, but it's still not suitable for cryptography. We can still recover seeds. So how do those work? Well, a lot of times the seed is just very poorly chosen, and this is true of pretty much every major programming language I know of. Ruby, Python, PHP all use a combination of time in milliseconds, the PID. Sometimes people will like read from stack memory and then throw that in, even though that doesn't. I mean, that varies, but it's certainly deterministic. Or they'll use a combination of these, or they'll use a hard-coded random value, which is what Sony did on the PlayStation 3 very famously for their ECC. So they were calculating signatures on all their binaries on the PlayStation 3, which requires a random number, but since they use the same random number every single time, you can actually calculate their private key, and this was done in 2010 by a group of researchers.
This is a relevant XKCD.
Yep.
It's funny, but at the same time, it kind of cuts to the heart of like what randomness is too. Like, it just returns 4, and it might actually take you a little while to realize that this wasn't a random number generator, or that it's just a really poor one, perhaps.
Yep.
Because it's entirely possible that you have a very large stretch of the number 4 in the middle of a legitimate, even cryptographically secure random number generator.
And that's really what pseudo-random number generators do, is they stretch entropy. So we have a little bit of hopefully truly random data for the seed, and then we stretch that entropy across a very large sequence. So now Dan is going to talk about attacks against random number generators.
Sure. So we're going to, some of those properties of random number generators are all the things that are potential weak spots that we can attack, right? So the first thing that you might be thinking about doing for attacking random number generators is the seed, right? So if the seed is the single value that's going to determine all of the random numbers from the very beginning all the way to the end, then if we know that value, then we know the whole thing. So in most of the cases here, we're going to be trying to recover the seed, trying to find some clever way of taking empirical output from the generator and getting the seed. So the first way, obviously, is just to guess what the seed value is. And in many cases, that's really possible. So they're 32-bit seeds, 32-bit integers rather, are the seed values for pretty much every generator, like glibc rand, the Mersenne twister, pretty much all of its variants, the Windows libc rand. They're all 32-bit seeds, just an unsigned integer or a signed integer. It doesn't matter, so they're 32-bit in. So there's 4.2 billion values there, which is not a whole lot of entropy. So that's something that can absolutely just be brute forced right off the bat, right? So that's certainly within the tolerance of an offline attack. So that's also important here, is we're not talking about online brute force attacks. So like often with password-based systems, if you want to try to guess somebody's password, you actually have to send a request out to the web server and say, is this the person's password? No. Is this the person's password? No. And that kind of thing fails because you have to wait a really long time for the request to come back, and then you might have the server like timing you out or something like that. So this is obviously only an offline attack, so we're not going to be doing any like cumbersome requests out to a server. So because we can do this all out, it's just limited by CPU power, and even a regular laptop is able to brute force through 4.2 billion values in a reasonable amount of time. Certainly within the amount of time that'll finish within an ordinary pen test. And also timestamp-based seeds. So the 31 million values is the number of seconds in a year. So that's a much, much smaller value, right? Do I see a hand? Sure, I'll take a question. So the question was, have you tried using Amazon to guess any of the seeds? We have just been using our own CPU power and laptops. Yep. If you really wanted to increase
I'll talk about distributed computing for breaking this stuff at the end, too.
Yeah,
so.
at least in practice, just using a regular laptop has worked for me so far. That it hasn't. The brute forcing does help the bigger, more powerful machines you have, especially if you're talking about a greater depth, which is something I'm going to mention in a little bit. Yeah, for obvious ordinary use case, pretty standard machines are good enough. So yeah, timestamp-based seeds, especially like Unix timestamps where it's 1 per second, is very, very easy, right? Even if you know the broad uptime of the server, which by the way is often given to you in HTTP headers, like the uptime of the server, you can give a pretty good idea of what the timestamp is going to be that was for the generator.
A lot of times it also give you, the web server will be very helpful and tell you how long it took to process a request. So you can start with the HTTP response time and then count backwards that many milliseconds or whatever. And if the seed is based on time, it's going to have to occur within that time frame. So it's very easy to narrow down the seed.
And even some of the other values that we talked about, like process IDs, things like that, are not very random at all. Process IDs tend to be very short. If you ever just look at a random process ID on your computer, if they're a very short number, you can enumerate all through not all possible process IDs, but through all extremely likely process IDs very quickly. Weakly or poorly chosen seeds are the #1 way to break a random number generator. We provide an easy framework for doing that with trying to match as many different algorithms as possible. So we're going to talk a little bit about here the actual algorithm that's used to check whether a particular seed is correct or not. So we have a set of given numbers. So here they're just 2-digit numbers. In reality, they're going to be much larger than that, but this is a good visual aid right here. So like 42, 61, 27, etc. In case you couldn't read that. We're just going to say these are our given set of observed numbers from the random number generator. So suppose you're on some site and you see those are the document IDs that are getting thrown out from some website that's storing documents online. So we try a seed. We just say we're going to try seed number 100, right? So we calculate what the random numbers should be one by one, and compare it to the head of the list here. And I'll have a little animation in just a moment. If it matches, then you move to the next number, and you can just continue until matches have been found. So this has a great property, which is that it doesn't matter if our numbers are out of sequence. So here you can see. Let's see, can we back? Oh, is it just going automatically? Okay. Go back. Yeah, so suppose we have 42. So the top line is our observed numbers, the numbers that we've just seen from whatever website we're attacking. And so the bottom numbers are the random numbers that are being output by our generator, right? So for any particular seed. So what we're going to do is we're going to try getting a first number. The first number is 45. That's not the right one. The next one's 33. Not the right number, right? 42. Aha, we got the right number, 42, right? So that's a hit. So now we look for the next number. So 97 is a miss, didn't get anything there. 61, aha, that's a hit. So we move on ahead again. So then we say 27, that's another hit. So we move forward a little bit. 75, we get another hit. Our error's a little bit off for some reason. 49 is a miss, that's not a big deal. We just keep moving. Like 51 is another miss. 89, there we go, there's another hit. And then you keep on going until you get to the end. So what's notable here is that this means that the numbers that we observed from the website, right, the top number, are not sequential. And so that's a really big deal for making this attack realistic, making it weaponizable. Because if you're grabbing IDs from a website that's live, then chances are you're not the only one getting values from the generator, right? There might be just other users that are going to be, getting other random values from this thing. So like in the middle there's going to be this entire chunk of somebody else who uploaded a document. Now that's their number, right? So requiring sequential numbers, we try to avoid at all costs. So that's something that we do here with this, quick little algorithm. And we'll be able to predict everything from then on because we have the entire internal state, right? Because any number is defined as just the sum of the two previous numbers, but only going back as far as 31 spaces. The only trouble here is that we're missing the LSBs. So if you just try straight up adding the values that you see, they're going to be off by like 1. And then the next time you try adding them, they're going to be off by 2. And the next time they're going to be off by 4. And pretty quickly, they're going to be totally different numbers. So we have to do some fancy math to try to recover the LSBs. But minus that, the basic algorithm here is pretty straightforward. You just observe 32 consecutive numbers anywhere, and then that's it. That is the internal state. And so you never actually get the initial seed from this, which is sort of interesting. All you get is a state, and then from the state you can go backwards and forwards to predict all future and past values. So grabbing the least significant bits, there's kind of two methods that we use. There's the guess and check. where you take the internal state, you assume that all the LSBs are 0, right? And then you just see how well does that predict all the numbers that I've observed. And so you get some measurement of how well that predicts my random numbers. And then you try flipping a bit and see if that improves or makes your prediction worse. And if it made it better, then you keep that increment, right? So that works somewhat well. And then there's the Boolean algebra way, which we also do, which is, I think, a little bit too mathy for this. It would be really long. But yeah, the LSBs are essentially like a big Boolean equation where you know that these two values have an OR relationship, and it also has an XOR relationship, and these two numbers have an AND relationship, and so you can just map that out and take care of it like some giant Boolean equation. Though it is notable that you do actually need more than 32 consecutive integers for this to be completely sure. If you have less than, I think it's 132, if I remember correctly, then it's possible to get a false positive, where you'll have an internal state that says, here it is, it perfectly predicts all the numbers you've given me, but if you were to try that against the actual website again, then it might start differing. So if you can get the more consecutive numbers, the better for doing this kind of attack.
Just like with anything in pen testing, the more information you have about a target, the more accurate you can exploit something. So.
Yeah.
All right. So the core application is written in C++. I much prefer Python to C++ and C, just because it's more fun and I don't have to worry about like memory and stuff. So we've gone ahead and written Python bindings for this application as well. As you saw before, we have a command line interface, so you don't have to even worry about all the stuff we just talked about. You just have to get output from the random number generators and then let Untwister do all the math and stuff for you. But let's say, if you wanted to distribute this on Amazon EC2 or something like that, in C++ world, you're going to have to write like OpenMPI bindings or something like that, which can be very troublesome and annoying. But C++ does, however, something that Python cannot, and that's in the threading. So in the C Python implementation, there's something called the GIL, the Global Interpreter Lock, which basically prevents Python bytecodes from executing concurrently. And basically what this means is that threads in Python are not performant. They won't consume multiple cores if you want to, if we're interested in performance. Threads in Python are still useful for certain things, but not for utilizing multiple cores. But this is something C++ can do very easily because it's native code. So what you can do is, and this is what we do in Untwister, is you basically define a Python interface to your C++ code and suspend the Python execution and then let your native code run and then restore the Python thread state after you're done. And this allows us to call a Python function which executes C++ code on multiple cores, but we get back a Python object and it's completely transparent to the Python code. And what this is really powerful for is we can do something like rpyc, which is remote Python call, which basically allows you to call Python functions across a network. And so basically we can set up a server with multiple nodes, call a single Python function which will execute C++ code on multiple threads across multiple machines, and it just looks like a normal Python function. It's very, very simple, and I'll demo this in a second too. So the code is available on GitHub right now on any of those repos. Bishop Fox is the company. Alta4 is down here. Moloch, decrement, I guess. So you can find that the latest code is probably...
it's up on the Bishop Fox GitHub account,
Yep.
so you just go to github.com/Bishop Fox, and you'll see Untwister there in our repos.
So...
Well, the Python bindings are also worth mentioning for output mangling.
Oh, yeah. We can get to that. I'll demo it here.
Okay.
So, as you can see, we have an Untwister SO. This is just a normal shared object, similar to a DLL, if you're familiar with that on Windows. So what we can do is we can import this shared object just like anything else. So we just actually imported that shared object, even though it doesn't contain any Python code. It's just a C++ shared object. And we even get doc strings and stuff which describe it. It's just like a normal Python function. And we can... So this is a test script which is equivalent to the command that I ran earlier. And as you can see, this is all the code that we have. And it just looks like normal Python code. But when we run it, it actually returns a Python object, which is a list of tuples with the seed and the confidence. So we can manipulate those just like any other Python object, even though we're calling C++ code. And the C++ code will actually throw Python exceptions too. So if there's a mistake or something, the C++ code will throw a Python exception, and we can just have all of the logic for that handled in our Python code, and we don't have to write any C++ code and have to worry about recompiling stuff and then linking it against the proper libraries and whether or not we're performant or not. It's all handled by the C++. And we maintain multiple threads of execution with this model as well. So,
the confidence levels, I think, is something we didn't mention that bears mentioning. So the confidence levels are based off of how many of the correct hits we got. So we have an initial set of observed values, right? And perhaps we just didn't go deep enough or something like that. And we observed half of the values, but then we didn't see the second half, right? So we say, well, we're starting to get right values, but we didn't get all of them. So it might have a confidence level of, say, 50%. So if you see a confidence level of 100%, that means we, in fact, predicted all the observed values. So the confidence level is sort of what it might sound like. It's kind of how sure the program is that this is the correct seed. And you can set that to various thresholds if you want to only give me outputs that are 100%, or maybe if you only get a couple of outputs, then that's good enough for me.
It's also worth mentioning that in a lot of interpreted language, while the underlying system may use something like the Mersenne twister, you're not really calling, so for example, in Python, the Python rand function uses Mersenne twister, but Python doesn't have 32-bit integers, right? Integers in Python are arbitrary precision, so there's actually some XORing and stuff that happens when you call random.randint, which returns a random integer between a certain range. So in the field, you may need to add logic in front of or behind the actual brute forcing of the seed. And that's another thing that this Python interface is really good for. We're also going to pretty soon we'll have support for tamper data scripts. So you can define a Python callback to manipulate the output before we compare it against the list of observed values. And that's how you can break that random.randint sort of stuff. So.
No. I guess that's about it. Yeah, we have our contact information at the end of the slides here. I guess it bears mentioning that we're hiring, so if you ever felt this was super cool and wanted to work, then that's worth it. Then we'll take questions. A question?
I've got a microphone. Hold on.
Okay, good. This will be better than me having to repeat, probably.
You mentioned that the depths can be selected by the person running the script.
Yeah.
In your experience thus far, what kinds of depths have been typically required to get various levels of confidence in the data returned?
Yeah, I think that in the instances that I've used this for actual pen tests, have been on test environments, not live production machines that have been running for a really, really long time. So the depths have been pretty short. So 10,000 or something like that has been pretty sufficient. So this, on a QA environment, that's not going to get a whole lot of traffic. And of course, dependent on the context. If you're doing things like password resets, and that's a pretty uncommon thing. That's not going to happen very often. So even on a production system, you're going to get, maybe a few dozen or something like that a day, depending on the size of the site. So it's even hard to give you a ballpark. But on something that might be if you even just visit a page and then that, gets a new random number, then that's going to happen all the time. You might be getting tens of thousands of hits per hour, or I don't know, right? So that it's really hard to say, for instance. But yeah, in the instances that I've done it, on non-production systems, on relatively quiet boxes, 1,000, 10,000 is pretty sufficient. And that's something that's enumerable on a pretty ordinary laptop too. So. So.
I was just curious what the Moloch affiliation is. Is that just a name you guys made up, or is that the AOL packet capture?
No, I had it before AOL, for the record. It's a reference to Buffy the Vampire Slayer, which is a TV series, and there's a demon that gets uploaded to the internet. So.
And my name is a reference to a hotkey that makes your programs go faster. You should try it sometime.
Yeah, with all these random number issues, wouldn't it make sense to just always use secure random number generators, or are there serious performance issues? And there's recently been a debate that Linux should get a random number syscall.
Yeah.
So do you think this will change things? And because I think it may just make sense to say all programming languages should always use secure random number generators, and we are done, and we don't have this problem.
Yeah, that's a really good point about I actually saw the patch file for that, the Linux kernel system call for like get random numbers. I think that's a great thing because in many cases people want to do the right thing, like they want to use secure random numbers like on their embedded environment or something like that. But then you just have a logistical programming problem of like how do you actually get it? You want to read from dev-urandom, but like maybe dev-urandom doesn't exist in your system, so you try like dev-random, but you really shouldn't be trying dev-random. Maybe it's in the proc file system, or who knows, right? Like what do you do? So there's a lot of, like I think OpenSSL had a famous problem where like they tried all these things. They tried like dev-urandom, then they tried dev-random, and then they tried something else, and eventually defaulted down to something like really horrible. That's like wasn't random at all. And
That's where the stack memory came from.
Exactly, right. That got them into like a lot of hot water. And so that sort of thing can be alleviated by just having a system call in the Linux kernel that says, give me some random numbers.
Yeah, the nice thing about random numbers in a program is that they're very easy to swap out, since you shouldn't know what they're going to be anyways, hopefully. So yeah, it really does, I mean, for probably like 99% of the use cases of random numbers in applications, you can use cryptographically secure random number generators. It's just that developers aren't aware of the problems with like default rand or random in Python and things like that.
And partly there is some legitimate doubt being put on to whether or not these things have been exploitable, right? That's kind of the thrust of our tool Untwister, is that these problems have been well known for a long time, and we want to make that clear that like there's not any new like theoretical ground being broken here. Like this is really just an implementation of attacks that other people have done, or an implementation in a way that's actually usable from a real pen testing perspective.
The only time you really should be using pseudo-random number generators, or like not cryptographically secure pseudo-random number generators, but like Mersenne Twister and stuff, is if you need a random sequence to be repeatable. So for earlier we talked about John von Neumann and his calculations related to the hydrogen bomb. So he needed to rerun calculations on something that seemed on the same sequence of randomness each time. So if you need the same sequence of random numbers every time, that is a definitive use case for pseudo-random number generator. For pretty much anything else, you should be using a cryptographically secure random number source.
So like video games, for instance, like if you want to have like some random numbers being generated every time you shoot a gun, like whether it goes up or down or something like that, right? The bullet spray or how much damage you do or something like that. But then you also want to be able to take a save file and replay it from start to finish. That kind of means you have to use a deterministic, like insecure random number generator. You can't use truly random numbers each time, otherwise like you wouldn't be able to, unless you saved all of them individually.
Yep.
Yeah, you could, that's correct. You
Although
could use
most secure random number generators will not allow you to control the seeds because they'll use entropy pools. So they'll be pulling they'll basically be pulling seeds from multiple areas and then mixing them into a pool of entropy. So like, or at least hopefully.
And to a point you made earlier, there actually are potential performance hits that you can take on secure random number generators, especially if you have to go through the system call interface. And then that's going to be a bit of overhead in a way that you're not going to be hitting by just calling a library call. But for the vast majority of instances where you really need secureness in your random numbers, like that tiny bit of system call overhead is not worth the risking of your data. Especially if you're talking about password resets or something like that happens so infrequently to the point of it being a negligible amount of performance hit. We have other questions? Yes.
Mike, from a practical purpose, which frameworks have you had success against? Are you just against custom applications, or have you seen third-party frameworks that are falling down on this kind of stuff?
So the default PHP, so PHP does both like rand and empty rand by default, like the Mersenne twister. One of the challenges we've had, however, even within the Mersenne twister itself, is that like the slightest of differences in like how it's set up or the actual algorithm causes it to be totally different numbers, to the point where it's actually hard to reproduce. So in trying to implement the PHP's Mersenne twister, I literally just copied out the source code from like the PHP source, because of course PHP isn't written in PHP for obvious reasons, right? It's written in C. So I just literally.
There is a version of PHP written in PHP.
I wouldn't recommend it. The actual C file, like when I took it, copied it into my own program and ran it, gave me different numbers than a PHP program was, and I could not figure out for the life of me why it was doing that. Because the tiniest of differences in terms of implementation will cause you to get totally different numbers. But yeah, in terms of actual successes, PHP has been really good, and then of course local like desktop apps or anything that's native code running, particularly glibcrand, is something that's like really easily supported. As a source of that problem, as you were saying, ASLR?
Yeah, ASLR is generally just I don't believe you actually even need to use cryptographically secure random numbers for the ASLR slide. I mean, it's probably a good idea too, but really the idea of ASLR is that the shift is just indeterminate at the time that you're like injecting shellcode into a process. So usually the entire memory space is shifted only one value, and then use offsets and stuff like that.
Even then, I mean, that would matter if you're trying to seed on the basis of like stack memory.
They're probably just calling. I would assume on Linux it calls dev random and stuff. So,
yeah.
But yeah, that isn't really a use case that we have for this application, just because breaking ASLR is very contextual and dependent on like what libraries and stuff you have available to your shellcode and stuff like that. So you have to like find a leak and then calculate the offset or calculate the slide and then jump to something. So it's not really something that this is meant to solve. So
maybe time for one more question, if any.
Additional question?
Okay. Thank you very much, gentlemen.
Excellent. Thank you.